Now, since we have studied all the applications and theoretical aspects of analogies, it is time to incorporate them and use them to solve some numerical problems. The very first question, which is going to be here, goes as follows: 100 kg of water evaporates from a wetted surface of rectangular shape when air at 1 atmosphere and 35 degrees Celsius is blown over the surface with a velocity of 10.42 meter per second. Heat transfer measurements indicate that the air at 1 atmosphere and 35 degrees Celsius. The average heat transfer coefficient empirical equation is given below, where H is in watt per meter square Kelvin, V infinity is the air velocity in meters per second. Estimate the time in hours to evaporate the complete water if area is 1.3 meter square. The empirical equation given is H equals to 21 into V to the power zero point 0.8. Let us now understand what the problem says. We are given a mass of water which is of 100 kg, which is evaporating from a surface which is rectangular, where the pressure is the atmospheric pressure and the room temperature is 35 degrees Celsius. Now what has happened is air is blowing with a velocity of 10.42 meter per second, and we have a relation given for us to calculate the heat transfer coefficient. The physical properties which we are going to use for solving this numerical problem are: for water at 35 degrees Celsius, the PSAT is 0.0562 bar. The DAB at 2.88 into 10 to the power minus 5 meter squares per second at 40 degrees Celsius. For air at 35 degrees Celsius, density is 1.1460 kg per meter cube. Kinematic viscosity is 16.47 into 10 to the power minus 6 meter square per second. And Cp is 1005 joule per kg Kelvin, and Prandtl number is given as 0.71. Let us start the solution for the given problem. We have the given data as stated above, and mass is 100 kg. Let us now use the empirical relation, which is H equals to 21 into V infinity to the power 0.8 to get heat transfer coefficient. Already the velocity is given as 10.42 meters per second. Substituting the value of velocity in the empirical equation, which gives H equals to 21 into 10 to the power 10.42 to the power 0.8, which gives 136.93 watt per meter square Kelvin. Also, we can calculate Schmidt number, which is given as kinematic viscosity by DAB. But the DAB, which is the mass diffusivity, is given at 40 degrees Celsius. We need to calculate it at 35 degrees Celsius. And we know from the empirical relation and formula, d2 equals to t1 multiplied by t2 by t1 to the power 1.75 is the empirical equation for calculating mass diffusivity at different temperatures. Since 35 degrees Celsius is 308 Kelvin and 40 degrees Celsius is 330 Kelvin, we have substituted them in the equation as given shown in the page. The value of DAB has been calculated to 2.80 into 10 to the power minus 5 meter square per second. The same value has been taken to calculate Schmidt number, which is mu by DAB, which is 16.47 into 10 to the power minus 6 divided by 2.80 into 10 to the power minus 5, and the Schmidt number is found to be 0.588. Now, since Chilton-Colburn analogy has to be used because Prandtl number and Schmidt number are not equals to 1, which is generally considered in case of Reynolds analogy. Hence, we cannot apply Reynolds analogy to this problem. The Chilton-Colburn analogy formula, as we know, is Stanton number to the heat transfer multiplied by Prandtl number to the power 2 by 3 equals to Stanton number for mass transfer multiplied by Schmidt number to the power 2 by 3. Substituting the formulas which we know, that is Stanton number for heat transfer equals to H by rho CPV multiplied by Prandtl number to the power 2 by 3, which is equals to Km by V to the into Schmidt number to the power 2 by 3. Since velocity is common in both the sides, LHS and RHS, so it can be cancelled. Hence, the formula can be simplified as Km equals to H by rho Cp into Prandtl number by Schmidt number to the power 2 by 3. We had all the given data, which is Km equals to 136.93, the value of H, divided by rho, which is 1.1460, multiplied by Cp, which is 1005, and Prandtl number 0.711, Schmidt number 0.588. Calculating this, we get Km as 0.115 meter per second. Now, calculating Csat, the concentration at saturated pressure, gives us Psat by RT. Since the pressure is in bar, so we have used the value of R as 0.082. Hence, after calculating it, which is 0.0562 divided by 0.082 multiplied by temperature, which is at 35 degrees Celsius and is taken as 308 Kelvin, gives 0.0022 mole per liter. Converting this to mole per meter cube gives us 2.22 mole per meter cube. Now converting this to kg per meter cube by multiplying by mass of water, 1 mole is equals to 18 units. Hence, this gives us as 0.03996 kg per meter cube. Now, calculating the molar flow rate, which is Na, is Km into Csat minus 0, which is equals to 0.115 into 0.03996 minus 0, which comes out to be 0.00454 kg per meter square second. Now calculating the mass flow rate is Na multiplied by the area, which is given in the problem, which is 1.3 meter square. Multiplying this to 0.00454, we get the mass flow rate is equals to 0.00590 kg per second. Since we have to calculate the time and we have been given initial mass as 100 kg, which can be calculated as mass by mass flow rate in terms of seconds. So time is equals to 100 kg divided by 0.00590 kg per second. Hence, the time comes out to be 16949.15 seconds. Converting this to hours by dividing by 3600, the time comes out to be 4.70 hours. Hence, this is the solution to this problem where we applied Chilton-Colburn analogy. A few points which we need to remember while doing the calculations where generally mistakes can be made is using the correct analogy as well as using the correct value of DAB at 35 degrees Celsius, since in the problem it is mentioned at 40 degrees Celsius. If we keep these two things in mind, we can get the correct answer. Also, do not forget to convert into appropriate unit for Csat in terms of kg per meter cube, because the mass of water is 100 kg. You cannot take it in terms of moles, otherwise your calculation will go wrong due to not balancing the dimensions. So the very first problem which we have a look, the numerical problem after the theoretical one, is done. And now let us move forward to another problem which will be taken by my friend Vedant. Thank you.
So hello everyone. Now we will look into our next question. The question reads like this: water evaporates from a wetted surface of rectangular shape, and the flow rate at which it is evaporating is 14.9 kg per meter square hour. It is the flux. Then, when air at 1 atm and 35 degrees Celsius is blown over the surface, diffusion coefficient of water in air at 50 degrees Celsius is given as 1037 centimeter square per hour. If thermal conductivity, density, and specific heat of air at 35 degrees Celsius is 0.016 joule per minute per centimeter per Kelvin, 1.1460 kg per meter cube, and 1.005 kg per kg Kelvin, respectively, and the saturated pressure of water at 35 degrees Celsius is 0.816 psi, we have to find out the average value of heat transfer coefficient over the area in watt per meter square Kelvin. So, what is happening in this question is we have been given a rectangular wet surface of which the flux at which the water is evaporating is also given as 14.9 kg per meter square per hour, and then we have been given at 1 atm at 1 atm and 50 degrees Celsius the diffusion coefficient as 1037 centimeter square per hour. We have been also given the thermal conductivity, density, and specific heat of air at 35 degrees Celsius. So let's see, note down what is given. The flux, which is given as 14.9 kg per meter square hour, we will convert this into kilomole per meter square second, which came as 2.299 into 10 to the power minus 4. Now we have been given the diffusion coefficient at 50 degrees Celsius, that is 323 Kelvin, and that is given as 1037 centimeter square per hour. We will convert this in meter square per second for our convenience. That came out to be 2.88 into 10 to the power minus 5. Now we need the value at 35 degrees Celsius, since everything our values are given at 35 degrees Celsius, that is 308 Kelvin. So we will use other relationship between temperature and diffusion coefficient, that is DAB is directly proportional to temperature to the power 3 by 2. So if we use this relation, we will get as our DAB at 308 Kelvin equal to DAB at 323 Kelvin into our temperature, that is 308 Kelvin by 323 Kelvin whole to the power 3 by 2. If we solve that, we get our final value of diffusion coefficient at 308 Kelvin as 2.6891 into 10 to the power minus 5 meter square per second. Now we have been also given the thermal conductivity, that is 0.016 joule per minute centimeter Kelvin. We will convert this into joule per second meter Kelvin, and that came out to be 0.0266. Next, the density will remain same, 1.1460 kg per meter cube. The specific heat is given in kilojoule per kg Kelvin. We will use it as 1.005 into 10 to the power minus 3 joule per kg Kelvin. Then the PSAT, the saturation pressure, we have been given as 0.816 psi. We will convert this into bar so that we can calculate the Ca saturation. So the pressure in bar is 0.05626 bar. So we will use the formula of CA is equal to P saturation upon gas constant R into T to calculate our concentration at saturation value. So this saturation value concentration is the concentration near the plate wetted surface. So if we substitute the values, we will get the Ca saturation as 2.224 mole per meter cube. Now we know from the Satry equation the mass flux that is average mass transfer coefficient into Ca saturation minus Ca infinity. We assume Ca infinity as 0. Now we will substitute our values of mass flux which was given, that is 2.299 into 10 to the power minus 1. We converted kilomole into mole, so that is why 10 to the power minus 1 is equal to mass transfer coefficient into 2.224 minus 0. So the mass transfer coefficient average value came out to be 0.1033 meter per second. Now we will use Chilton-Colburn relation so that we can get our value of heat transfer coefficient from mass transfer coefficient. So the Chilton-Colburn relation is given as Stanton number of heat transfer into Prandtl number to the power 2 by 3, which is equal to Stanton number of mass transfer into Schmidt number to the power 2 by 3, where the Stanton number is given as average value of heat transfer coefficient upon density into heat capacity into characteristic velocity. The Prandtl number is mu viscosity into heat capacity upon thermal conductivity. The standard number of mass transfer is given as mass transfer coefficient average value upon characteristic velocity. The Schmidt number is given as kinematic viscosity upon diffusion coefficient. So we will substitute these formulas in our Chilton-Colburn relation. So it so since we don't require the viscosity of this in this question, so we will cancel it in the first place from our equation relation, and we also don't need our uh, characteristic velocity, so we it can be cancelled because of the equation. Then we substitute our values of thermal conductivity, which is 0.0266 joule per second meter Kelvin, our density as 1.1460 kg per meter cube, our heat capacity as 1.005 into 10 to the power 3 joule per kg Kelvin, our and we will substitute our value of diffusion coefficient at 308 Kelvin, which came out to be 2.6891 into 10 to the power minus 5 meter square per second. And lastly, the mass transfer coefficient, which was 0.1033 meters per second. So after substituting all the values, we get the heat transfer coefficient as 107.56 into watt per meter square Kelvin. So how this problem differed from the last question was because we have been not given the value of Prandtl number and Stanton number, so we Schmidt number, so we substituted their formulas, that is Prandtl numbers mu into Cp by K and Schmidt numbers kinematic viscosity upon diffusion coefficient. When we put these formulas in the equation, we can see that the viscosity term was cancelled on each side, so we also didn't need the viscosity, and the characteristic velocity, which was also not given in the question, was also cancelled in this equation, so we also didn't need that. So we used the Chilton-Colburn relation because for as in instead of Reynolds analogy, because in Reynolds analogy we assume the Prandtl number and Schmidt number as 1 for gases, but here we have been given the values and we have also been given the relation. That's why we use the Chilton-Colburn relation. And if we look at some mistakes which can happen in this question, can be the unit conversion, because we have to keep our units consistent throughout the question. And also a major mistake students can commit is regarding the value of diffusion coefficient. We have been given the value of diffusion coefficient at 50 degrees Celsius, so we have to convert it into 35 degrees Celsius as our values are given, the properties are given at 35 degrees Celsius. Now we are done with this problem, so let's move ahead to our next problem. Let us move ahead.